Okay, well, hi everyone. Welcome to the last week of classes. It's finally here. Um, okay, so maybe what I'll do is I'll start with like an overview of what the rest of this course is going to look like, just kind of what the next week is going to be like, basically. So today we're going to learn about a design pattern in algorithms and programming called recursion. Um, and so that'll be the focus of today's lecture. Um, there'll be an assignment today, as usual, based pretty much entirely on the stuff that you're going to learn today. So it won't be like a full week's content worth of assignment, and the same will be reflected on the quiz. And then on Wednesday, we'll just review. We'll have like a review day where we go over the assignment problems that are going to be released today. And then on Friday, I'm very, very excited to announce this. We are going to have four mini guest lectures from grad students in the CS department working in a variety of areas, some of whom are good friends of mine, some of whom just offered to help when I sent out the email. And they're going to be showing you some of the many cool things that you can do with all the programming that you've learned in this course so far. So stay tuned for that. That'll be Friday's lecture. And then the quiz. So the quiz on Friday will cover, like, it will have a question probably about like this recursion stuff that we're going to go over today. And then it'll have some bonus questions based on the little mini guest lectures that you're going to see on Friday. But they won't be anything like super technical about it. It's just like, I don't know, like, did you show up and pay attention, basically? Like it'll be that level of depth in the questions, essentially. So yeah, that's the program for the week. Any questions about what's on the menu, what we've kind of seen so far? Oh yeah, quiz solutions will also be posted today as well for Friday's quiz. Um, yeah, any questions about anything about no? Doing good? Okay, great. In that case then, let's get started. So, how do I want to do this? Yeah, we're going to, as I mentioned, we're going to look at a design pattern called recursion today. And we've kind of um, teased, like there's been a little teaser trailer of what recursion is like when we were looking at some of the binary tree stuff. And the basic idea behind recursion is when I want to solve some problem, um, sometimes the most intuitive way to do it is to break it up into one or more identical subproblems, solve those, and then use the solutions to those problems to solve the original problem that I wanted to solve. I mentioned this briefly when we went over merge sort last time. That's an algorithm that we're going to see in a little more detail towards the end of the class today, once we are more familiar with this recursion design pattern. But this is the basic premise of recursion, really. It's not super difficult to state. What is kind of difficult is just wrapping your head around it the first time you see it. But once you can do that, you'll see that like it's very, very approachable. And it's a very nice design pattern. Like you'll start thinking of problems in new ways, like approaching them in new ways and you'll see the world with the recursion glasses on. And it really jumps out at you to solve certain types of problems. And to kick off today's lecture and actually give a concrete demonstration of what it is that I'm talking about, we're going to look at a very, very popular example that many of you are probably already familiar with, but maybe have never had the occasion to identify as recursion yet. And this is the Fibonacci sequence, right? Are we all familiar with the Fibonacci numbers? It's a very, very famous sequence of numbers. The basic idea is that um, the first Fibonacci number is, bless you, 0. The next one is 1. And then to get any Fibonacci number after that, you just add the previous two Fibonacci numbers together, right? This is how you get this pattern. And what we're going to do is we're going to see a recursive way of programming a function where when you give me some number n, I will give you the nth Fibonacci number. Okay, and we're going to do it recursively. So let's see how to do that. Um, I already have this nice stuff here. Okay, so I'll just call this fib.py. So we're going to make a new file. And as I said, we're going to have some function that we call Fibonacci. It accepts an integer n. And okay, now we want to compute what the nth Fibonacci number is. So when you're designing a recursive function, you'll notice in just the way that I stated it to you, how the Fibonacci function, like the definition that I gave you was, I started with this base case, right? I said when n is zero, or I guess one technically, the first Fibonacci number, the zeroth Fibonacci number, is just zero, right? And then Fibonacci of one is just one. And then from there, we define all subsequent Fibonacci numbers as a function of preceding Fibonacci numbers. And so that initial case in the beginning, before you can actually like do this inductive definition, that base case is called, well, the base case, right? And in every recursive function that we look at, there's going to be some base case, which is in some sense the simplest subproblem, right? The thing, the really trivial thing that you do when you have a case that's like n equals one, or there's a single element in whatever recursive function you're looking at. So for the Fibonacci numbers, the base case is going to be, well, if n is equal to zero, then we just return zero, right? Otherwise, there's another base case. There can be more than one base case. The Fibonacci function is an example where there are two. If n is equal to one, then we return one, okay? So we have our base cases covered, right? And now all that's left is to do the inductive step, as it's called, right? So here's our base case. Now in the inductive step, this is the part of recursion where when you see it for the first time, you're like, huh? How does it, is this allowed? Like, can you do this? Turns out you can. What we're going to do is we're going to say return Fibonacci of n minus 2 plus Fibonacci of n minus 1. And that's my whole function. You'll see I'm calling a function within the function that I'm defining, right? And so you look at it for the first time, you're like, well, it's like circular, right? How does this actually work in practice? And the answer is it's because of the base cases, right? Like the reason why this isn't just circular and nonsensical is because when I call this, it'll look at subproblem where the input n is one less than it was when I called this function, and it'll keep, decreasing on each subsequent call, recursive call to this function, until I get to one of these two base cases when I say that the recursion bottoms out. Yeah? So, okay, let's actually see if this works and that I'm not just speaking gibberish at you. So here we're going to import from fib import Fibonacci. Okay. And now let's check. What is the first Fibonacci number? Well, zero. Okay, it's zero. One, we've handled our base case. Two, 0 plus 1 is 1, right? So that checks out. Three, oh, now it's 2, right? You just sum the previous two. Four, and this is exactly what we want to see, right? 5 is 5. 6 is 8, right? We're always just summing the previous two numbers. So the Fibonacci number, very, very clean illustration of a problem where recursion, it just kind of screams out at you as the solution, right? Now, I want to say for any recursive solution to a problem, there is an equivalent iterative formulation where you actually use a loop to solve it. And we could have written this Fibonacci function with a loop, right? We could have written an equivalent Fibonacci function with a loop. But a lot of the times you'll see that the recursive approach cleans up the design of the algorithm so much, like that to the point where when you even try to think about it in the iterative loop way, it gets very, very messy and counterintuitive. But yeah, for this kind of initial introduction to Fibonacci, are there any questions about recursion so far, or how this works? About we understand the base case, it's like an inductive step. Yeah. Okay, cool. In that case, let's take a look at a slightly more involved problem where it's another like textbook example of like where recursion is really helpful. It's called the Tower of Hanoi. And this is what I used to learn recursion back in the day when it really clicked for me, or the moment where it really clicked for me. So I'm hoping something similar will happen for you guys. But I can sit here and explain the Tower of Hanoi is a game. It's a very old game. And instead of sitting here and trying to explain to you what it is, I think it would be best if I just actually show you. Uh, I can pull up this, and then we'll go to tower, Noi. Come on. Here we go. So here's the game. You have three pegs, okay? And the goal, you have these like stacked disks, all right? And the disks decrease in radius as you go up the peg, right? And the goal is to move all of the pegs from the left peg to the right peg, one disk at a time, so that a larger peg is never on, or a larger disk is never on top of a smaller disk. That's the rule of the game, okay? So I can do this, right? And I can do this, but I cannot do this, right? That's an invalid move because the bigger disk is going on top of a smaller disk. Yeah? So, okay. Well, maybe three is a little counterintuitive on how to do this, but if I can go down, dang it. Why isn't this? Okay, it seems three is as low as it goes because I guess they figured two is too simple. But okay, imagine for a minute that we didn't have these two to kind of illustrate why you might want to think about this problem recursively. Um, Imagine for a second as our base case that we didn't have these two disks here. Okay, so this tiny little disk over here was the only one that we cared about. Well, if I were like, if that were the case, and I just wanted to move them to this third peg over here, it's really easy to see how to do that, right? You would just, wow, groundbreaking stuff, right? That's the whole thing. Um, so, and if I wanted to move two, like you could see that, okay, well, I would do this, and then I would do this, and then I would do this, right? But when you start getting to three, the simplicity of those early base cases really seems to fall off quite fast. Like already at three, you're like, okay, well, maybe if I, how should I do this? Maybe I put like this here, perhaps? Or does anyone have any suggestions on for the case of three, like where to move stuff? Yeah. Okay. Uh-huh. Yeah. And you'll notice that in this solution that you suggested, what did you do? You broke it down to the case where the problem was of size two again, right? You were like, now I've reduced it to this case where I only need to worry about moving two pegs to this peg after I've, or sorry, two disks to this peg after I've moved this one, right? So you can see the recursive subproblem emerge. Like the goal, the solution for this is always going to be first moving, if n is the number of disks I have to move, then the solution is going to be move n minus one disks to the peg in the middle, transfer the bottommost peg, and then move n minus one disks to the one on the right. Yeah. And the beauty of recursion is that I just get to assume that because it's n minus one and I've handled the base case, I'm going to assume that my algorithm almost magically, it seems, know how to do the n minus one case. And assuming that it can do this n minus one case as a black box, I, to handle the n case, just get to assume that. I take that for granted, and I just have to worry about moving this one peg over, right? Does this make sense? Like how like, it's the same thing with like any number of disks that you give me. Like my goal for however many disks you give me is just going to be move these n minus one things to the middle one, move the bottom one here, and then move the n minus one things onto the rightmost one. Okay? Yeah, question. Yeah. So you, well, you can solve anything with recursion that you can with a loop. Or sorry, you can solve anything with a loop that you can with recursion, but the other way is also true. Um, and the difference is just in how you think about the problem, kind of. Um, And the Towers of Hanoi is a great example to illustrate that because to solve this algorithm explicitly with a loop, it's not at all obvious to me. I don't know. Like there's this really nice, clean recursive solution, right, that I was able to explain to you immediately. But if you had to come up with a loop, right, that did this thing, I don't like there'd probably be a lot of like ifs and else, and it's just like not, it's not nearly as obvious, you know? So it's just a question of design choice, basically. There are different ways of solving the same problems. But even though they solve the same problems, it's quite funny that one approach at times can be so much more obvious than the other, right? Um, okay, so let's see how to actually code up a function that will give us the moves that we have to make to solve the Tower of Hanoi problem on n disks. Okay, so go here now, and I'm going to make this new file called tower.py. And then we'll define a function called Tower of Hanoi, and it takes n, the number of disks to move from peg 1 to 3. And what I want this to do is this will returns the sequence of disk moves to get n disks from peg 1 to 3. Okay? I will represent that sequence as a list of tuples of the form source destination for each of those two tuples. Okay? So, okay, how are we going to do this now? Well, what's my base case? That's the thing that you always should think to ask yourself. When you're solving a problem with recursion, always ask yourself, what is my base case and how do I solve it? Well, the thing that's varying, like before it was n, the actual Fibonacci number itself, right? But what is n in this context? Yeah? Right, right. So what would a very, very simple base case be? Yeah, if I only have one disk, it's like super, that's the whole solution, right? So in the base case, so if n equals 1, then what I'm going to do is I'm going to return the list containing only a single move, and that is the tuple 1 to 3. Okay? So and I will return as a list of two tuples of the form source destination, right? Okay, so we have our base case, right? Now we have to do the inductive step or the inductive case. Inductive case. And this is really the part where the magic of recursion kind of sets in. So suppose you know how to solve the Tower of Hanoi problem for the case where there are n minus 1 disks. Okay, I just give you a magic black box function or subroutine that can solve this for n minus 1. How would you solve it in the case of n? You kind of saw it a second ago here, right? Or like, okay, what I'm going to do is I'm just going to worry about assuming I can solve it with 2 disks. I'll temporarily move those 2 disks to what I'll call the auxiliary peg, right? The one other than the destination. And then I'll move the largest disk to the destination peg. Yeah.
Okay. We can only move one peg at a time, and so
Only one disk at a time, yeah.
like when we talk about moving the two into the middle one, and we have to do that in 2 steps. So when
Yeah.
we do the programming, we need to, is it conceptual or are we actually doing every single step?
Yeah, so you just get to assume that you have this function, Tower of Hanoi 2. Like, let's say we're designing Tower of Hanoi on input size 3 right now. The magic of recursion is you get to assume that you already have that function in the case of 2. right? So you just get to call Tower of Hanoi n equals 2, move from peg 1 to peg 2. Okay? And it will handle all of this stuff about like moving this to the rightmost peg first and then this back here for you. Okay? You don't have to worry about any of that. Okay? So the way this is going to look in our program is we're going to say, okay, so here's what you're going to here's we're going to make this list moves. Okay? And what this is going to look like, before we do this, we actually need to figure out what the auxiliary peg is. Okay? So we'll call aux. This is going to be equal to, see, here's the tricky part. If I want to call Tower of Hanoi recursively, then I need to be able to move to pegs other than the third and from pegs other than the first. So what we're going to do is we're going to define what's called a helper function that looks like this. Tower of Hanoi helper that takes n as before, but also a source peg and a destination peg. And this is the actual recursive function that we're going to design, where we'll have this base case. And we'll say, okay, then return source to destination, because we're handling the general case now. And in our original Tower of Hanoi function, we're just going to call Tower of Hanoi helper n1, 3. Okay, so now that I have this, I can do my actual inductive step. I'm going to say the auxiliary peg is going to be equal to, I want it to be the thing other than source and dest, right? The other peg, right? So if this is 2 and this is 3, then I want my auxiliary peg to be 1. Okay? If this is 1 and this is 3, then I want it to be 2. And so a neat little way of calculating that is I can say the auxiliary peg is going to be 1 plus 2 plus 3, which is just 6, but I'm writing it out to be a little more explicit here, minus source minus destination. Okay, this is going to give me what the auxiliary peg is. Yeah? So, okay, now that I know what my auxiliary peg is, I'm going to define this list called moves. And what it's going to look like is it's going to be, okay, Tower of Hanoi helper n minus 1 to the auxiliary peg. I'm saying temporarily move all the n minus 1 pegs on top of the largest, or all the n minus 1 disks on top of the largest disk to the middle one, right? And then we'll add, this little slash here just lets me do a sum across multiple lines. Then we'll add moving the biggest disk, right? So then we'll do plus source dest, right? And this is equivalent to the base case of 1, right? Okay, and once I've moved my largest disk, I now need to move the n minus 1 disks that I stored on my auxiliary peg onto the destination peg, right? So then we'll add Tower of Hanoi helper n minus 1 from the auxiliary peg to the destination peg. And then I just return moves. Okay? And there it is. That's my recursive Tower of Hanoi helper function. Are there any questions about what we've written so far before we go into a demonstration? Yeah. So is your question what is aux or how are we computing aux? Okay, yeah. So yeah, maybe it would be easiest to demonstrate. So here, aux is, I'm defining aux as the peg that is not my source peg or my destination peg. It's like a temporary storage peg that I can use, right? So for this case, the auxiliary peg is going to be 2, right? It's the thing in the middle. But as the problem size increases, well, actually here we can illustrate it this way. So the very first thing that when I call this recursive function, right? It's going to go, okay, it's going to call the helper, right? And it's going to go, well, for n equals 3, we're going to call Tower of Hanoi helper 2 from 1 to 2, right? So it's going to move these two here, then it'll move the big guy here, and then the other two there. But in order to do that, right, when it calls Tower of Hanoi 2, that in and of itself makes another recursive call to the case of Tower of Hanoi with n equals 1, right? So, okay, if I just want to move these two things here, then what I actually have to do is move this here first. I want to like illustrate the call stack somehow with a bunch of functions. I think it'll become clear once I actually run it, like what's going on. Oh yeah. Well, this is just like a way, this is just a convenient way of saying like okay, so when source is 1 and dest is 3, the ones cancel out and the threes cancel out and aux is 2, right? And when source is 2 and dest is 3, the twos cancel out, the threes cancel out, and aux is 1. So it's just a mathematical way of getting what the other peg is, basically. That makes sense. Yeah, another question? Oh, the backslash just lets you define a sum across multiple lines in Python.
Indentation error.
Oh, could it be that there's a white space after the slash in your code? Because it doesn't like that, I think. That might be after the slash. Yeah. Yeah, yeah, no worries. Um, okay, so this will all become clear once we actually run it, I think. Like what's actually going on. So we'll do this. Now we're going to say first of all, let's actually try and compile this. Tower.py. Okay, good. And now we'll do this, Python 3 from tower, import a bunch of stuff. Okay, so let's try the base case first. Tower of Hanoi 1. Oh, why isn't it returning anything? Oh, it's because I'm not returning here. Duh. Okay, so let's try that again. This Tower of Hanoi is not defined. What? Oh, it's because I didn't import it. Haha. Okay, so yeah, here it says, okay, for a single disk, move from 1 to 3. Nice. For 2, now it's saying do this, right? If I can actually move this over here so we can see what it's telling us to do. So now it's saying, okay, move 1 to 2, 1 to 2, and then 1 to 3, and then 2 to 3. Oh, wait, this isn't right. This isn't doing what I wanted to do. Oh, sorry. I thought it was with 3. Okay, thanks. Then yeah, with 2 disks, it's correct. Great. Thank you. Um, okay, and with 3, aha, now it's telling me to do this whole thing. Uh, but this is let's do something more complicated. Like let's do the case of 4. Okay. And now, just so that it doesn't end up looking like a gigantic mess, I'm going to say t is equal to iter of this. Oop, 4. Clear. Oops. Control L. And then next T. So this is just going to give me the tuples one at a time rather than vomiting them out all at once. Okay, so it's saying the first thing, move 1 to 2. There we go. The next thing, move 1 to 3. The thing after that, move 2 to 3. And so you can see it's done the base case, or it's done the case of n equals 2, and it set the auxiliary peg equal to the third one, right, as its temporary storage. Okay, the next thing is it's going to move 1 to 2, so here. Then 3 to 1. So now it's saying, oh, move this over here. 3 to 2, move this over here. Now 1 to 2. And now you can see it's done, it handled the case of n equals 3, right? Moving it to this middle peg. And now it's going to do 1 to 3, so we move this here. 2 to 3. So now it has to move, it's now calling Tower of Hanoi helper 3 to 3, right? That's what's going on under the hood. So 2 to 3. Did I do that already? Nope. There we go. Now it's saying 2 to 1. Now it's saying 3 to 1. So move this here. And you can see all the little recursive subproblems that it's solving along the way. Each time it's moving some substack of these disks into the correct place. 2 to 3. 1 to 2. 1 to 3. Whoop. And then 2 to 3. Yay, we did it. So you can see, like, even though it's doing something, like, it looks like it's doing something really complicated with the way that it's shifting the disks around, like in the intermediary stages of this, but it was so easy to program in contrast, right? Because we just got to assume that we could always solve it in the case of n minus 1. Yeah? Any questions about this? Questions about this kind of design pattern of recursion? Okay. In that case, oh yeah.
You know what I did, some sort of error popping up with my
Okay.
Is there a in the Tower of Hanoi helper that you put, is there a 1 or a 3 in the last command?
A 1 or a oh, here?
No, when you recall it in Tower of Hanoi.
Oh, over here. Yeah, it's 1 and then 3. Yeah. 1 and then 3. Any other questions about this? It takes time to wrap your head around recursion and recursive thinking, so don't worry if you feel like it's a little foreign and weird looking right now. Okay. In that case, I want you guys to try this now. We're going to write a very simple recursive function to compute the nth factorial. And we're going to break for 10 minutes while you guys try and solve this in small groups. I'll walk around and help people. And when we regroup, we'll see how to do this. But for those maybe who aren't familiar with the factorial, so n factorial is defined as n times n minus 1 times n minus 2 times n minus 3 all the way up to times 1, right? This is just the mathematical definition of the factorial. And what you're going to do is you're going to write in a new Python file that we'll call factorial.py. You're going to define a function called factorial that takes an integer n, okay? And this returns n factorial, which is equal to n minus 1, like the mathematical definition, times n minus 2 times 1. Okay? And there's a very, very easy way to do this with a loop, right? But the key thing here is that I want you to try and solve this recursively. Okay, so think about what is the base case? And then once I have the base case in the inductive step, assuming that I can solve it with n minus 1, or, any number less than n, strictly less than n, how do I solve the problem when it's equal to n, my input? Okay. So, okay, we're gonna break now. 10 minutes. So maybe at like 22 around then, we'll meet up again and I'll walk around the room. Okay. So question over here. Oh yeah. What's the question? Oh, I think it's because, so here, you're returning one instead of source destination. Question over here. Oh, okay, that's happening. That's just I wish it's coming. I don't know, I'm not. Well, I think it has to not. Um. You got return moves. Oh. Yeah, because it's trying to call plus some, it doesn't actually exist. Yeah, that's how it always works. Yeah. Or something. I think it should. Great, excellent. No worries. Hey. Any questions on here? Or doing good? I'll come back a little bit. We haven't maybe had too much time to think about the problem, so. Great. Here's the guy. 2, 3, 2, 0. Yeah. Oops. And then you're just gonna step through. So over here.
Yeah, so it's kind of like maybe when you design recursive function, it's useful in things like, okay, I know that somewhere after I handle my base case, I'm gonna make a call to that factorial. Factorial. N minus one. So assume you get that for free. How would you use this to compute return? Yeah, that's great. You can just do this and then return this times n. That's the whole thing. Yeah, yeah, because then with this call, it's gonna do n minus one times n factorial n minus two. That would be actually. Is it kind of clear to make sense? Nice, okay, great. Oh, just because it's kind of the, like, you get factorial of n minus one free, right? So if I give you factorial of n minus one, and I want to compute factorial of n, how do I go from point A to point B, you know, like. Yeah, yeah,
I feel like I was gonna do it, but it was too many, also did figure out, like, logic.
Anytime you have a recursive function, there's two things you do. First, you always have instance. Yeah, it's like the simplest problem where the solution is just trivial. So, yeah, in that case. Now. Like. Factorial. Well, you're gonna have some. No. Okay, now you're gonna, this is something like line, right? That's gonna be somewhere in the code that you write to return. How do I take this and get to the return value of factorial? You want to return n factorial. Yeah, but in that case, and for this case, it's just. That only run the t-squared anyway. So now I have to handle t-squared and any number.
What I was thinking first is like, oh, we just have some counters. Oh, we can see the but it's like, yeah, we have to use it and then that kind of stuff, but then you try again, like it's always and six minus. You know exactly n minus one times n minus. No, I will discuss. This extending this minus equals to 1.
Yeah, so you get that now, basically, right?
Yeah. Well, you think we want so much more and
Sorry, we're and you're trying to solve right now. And just do
that for sure. If you stay with.
The whole thing is nice. Like, I don't have some returns.
If they like pencil.
It's something I'm saying.
Yeah, that's sometimes.
It helps you.
Yeah, sure. So if you say I'm super influenced, maybe I times it's but if we did next instance as well. Then it will.
It's a really challenging.
It's gonna be hard. Before I get on this.
You got it? Okay, nice. I was wondering here, think we. Nice, I think there's like one slight.
Yeah.
Operator, or like an operator that's. Yeah, there you go, I got it. Great. Cool, we do it okay over here, we. Yeah, nice, that's exactly right, cool, good stuff.
No.
You over here.
Yeah, I still don't think I can go around and hold it like all you.
Yeah, I think that looks good.
And it's like, spin out of there. And I didn't always show. Like works. You're such a great.
Uh-huh.
Alright, good find it. It's like I was like, what? Take the elevator and then go all the way to PSN. Yeah.
I think I'll explain this, I'll explain this, okay, it's a good question. Okay, it looks like everybody came up with the correct solution, so nice. But maybe I think like a lot of people, it looked like they were like, okay, I have the correct solution. I don't really know how it's like what's going on though, basically. So maybe I could illustrate quickly something that'll help make sense of this. So I'll start by writing out what it actually is. So a lot of people have this. First, anytime you're designing a recursive function, you ask yourself two things. The first thing is, what is my base case, right? Here, the base case is just when n, well, for the factorial, there's two technically. There's like when n is 0, we return 1. This is just the way the factorial is defined, kind of. 0 factorial equals 1. And then there's the base case when n equals 1, where we also return 1, right? So I've handled my base case. Now, the second thing you ask yourself in the inductive step is, okay, I get factorial n minus 1 for free. And whatever I end up returning over here, I know that I get this for free, right? I don't have to care how it works. I'm just going to assume that it works for me correctly. So given this, how do I return the value of factorial n? Well, let's ask ourselves, what is factorial n? It's this thing, right? It's, oh, I'm sorry. There's a typo here. There should be an n right there. It's n times n minus 1 times this thing. Okay, well, I know that this is n factorial. And I know that n factorial, or n minus 1 factorial that I get for free is equal to n minus 2 or n minus 1 times n minus 2 up until 1.
So if I get this for free and I want to return this, what do I have to do? How do I get from here to here? I just multiply by n, right? So my return statement, what I'm going to return is factorial n minus 1 times n. That's it. That's my whole function, right? Okay, but how does it, what is happening though? What's going on here? So we work with a concrete example of like, let's do factorial of 4. And I'm going to simplify it so that I don't have to write a bunch. So what I call this function, it checks, am I in my base case? No, I'm not. So it then goes to the inductive step and it says, okay, what this is going to return factorial of 3 times 4, right? And then it makes the call to this function, right? And this checks, am I in my base case? No. So what this is going to return, right? What this ends up becoming is factorial of 2 times 3. It was a weird 3. And then there's this 4 from earlier, right? This is the recursive call that happens here. And now it calls factorial of 2. It checks, am I in the base case? No, again. So it returns factorial of n minus 1, 2 minus 1, which is just 1 here. So this is factorial of 1 times 2. That's what this becomes. Times 3 times 4. And when it calls this, well, I actually am in my base case now. So this just returns. So this ends up being this times this times this times this. And you can see as the recursion unwinds, I recover the factorial expression that I wanted to compute. Yeah? Cool. Okay, nice. Any questions about? Yeah.
We just one base case that n equals 0.
Yeah. So in order for this to work, like on all n greater than or equal to 1, yes. But the factorial function is technically defined for 0. So that's why I threw in this extra case of n equals 0 here. Wouldn't we? Oh, well, if we didn't, my concern is if we didn't, you're saying if we didn't have this n equals 1 step?
Yeah.
Yeah, because then I think that what it would do is on the case where it's 1, it would do 1 times 1 in the base case. So yeah, I think that would work. Like you could also do this without having this. Like I think this also works fine. Yeah. Cool. Okay. Yeah, thanks for pointing that out. You can also do it this way. All right. So we could do more interesting things with recursion. In particular, there's a really nice sorting algorithm that I feel like I keep wanting to present. And every time I do it towards the end of lecture and I don't have enough time to actually present it in its entirety, but we have 25 minutes now. I think we could actually do it. So we're going to try. And this algorithm is called merge sort. And it's asymptotically faster than insertion and selection, which run in O of n squared. This guy, merge sort, runs in O of n log n, which is very, very fast in comparison. And today we're going to see, I kind of gave like a high level overview towards the end of last lecture of how this algorithm actually works. But there's this really nice informative diagram that I found online, like a merge sort illustration to kind of explain what's going on. Let's see if I can find it again here. Oh yeah, it was this one. What? No, I just want to open the image in tab. Oh, come on. That's terrible. What about? If I visit this, is it gonna be bigger? Okay, yeah, that looks a little nicer actually. So this diagram kind of illustrates what's going on with merge sort. So the brief description that I gave last time, basically the way the merge sort is a recursive algorithm. It breaks our problem up into smaller subproblems, inductively solves those problems, and then recombines their solution to return the solution to the problem that you originally gave it. And the way merge sort works is it says, okay, we're going to call, when you call merge sort on this big list up here, it splits the list in half, right? And it says, okay, now I'm going to merge sort on this, and I'm going to merge sort on this, right? And then recursively again, so the base case for merge sort is when n equals 1. You can see here, when it gets down to like a single element, that list is trivially sorted. So it knows to just return that one element, and that's sorted. We're okay, right? But until it gets to that base case, it keeps dividing the list up that you give it into two. Like you can see here, it says, okay, split this into like 12 goes here, and now 8 and 9 go here. Split this up here. And then once it's solved all these simple base cases, now it begins actually merging them together. So it says, okay, assuming that these sublists are sorted, I'm going to merge them into this sorted list here. Okay? And it does that by just stepping through each of these sublists, going one element at a time, and inserting them into the correct place in this growing merged list, right? And once it's solved both of these subproblems, right? Like it sorted this and sorted this, then it combines them into this merged thing here. And it keeps doing that. It keeps recombining these sorted subproblems until it recovers the full sorted list on the full list that you actually gave it as input. Okay, this is how merge sort works. Very intuitive. Also very, very natural recursive algorithm, right? Very natural algorithm where you would want to use recursion to solve this because it's baked in kind of to the definition of the algorithm itself. So what we're going to see now is how to actually code this up, this recursive algorithm here. Okay, any questions about how merge sort works at a high level? Yeah. Oh yeah, so when it's odd like this, in this case, the way this algorithm, like this specific algorithm works is it's just the left sublist gets one fewer element, basically, when it's odd. And you can see that happens here, it happens here. But that's really a matter of convention. Like this would also work if it ended up going in the right sublist instead. Yeah. Cool. Okay. So let's actually try coding this up. So now we're going to have a new file that I will call mergesort.py. And okay, so we're going to define a function called mergesort. And now this is going to take a list, which I'll call LST. And I want to return the sorted version of this list. Now, for this problem in particular, it's going to be useful to have a helper function again. Okay, kind of the way that we did with the Tower of Hanoi. So the way my recursive helper function for merge sort is going to look is it's going to look like this. I'm going to say, okay, merge sort helper is going to work as follows. It's going to take the list and then an index low and an index high. And what this is going to do is it's going to sort the sublist from low to high. And it'll be low inclusive to high exclusive. So it's just, this is how we're going to break our problem up, is by just shrinking the range of low to high, right? Like I'm only interested in sorting this specific subportion of this list, right? And so what my full merge sort function is going to look like is it's just going to be, okay, return merge sort helper from LST 0 to the length of list, right? The whole thing. Just call the helper on the whole thing. Okay, great. Now, what is my base case? It's my, yeah? Yeah, exactly. When low is, it's just one thing, right? So the base case is going to be if, and we can actually, I'll define it here. I'll say n is going to be equal to high minus low. So this is just the number of things to sort in my sublist, right? If n equals 0, right, which happens when low and high are the same thing, so there's only a single element, then I just return, how did I do this here? Oh yeah, I do nothing because it's already sorted, right? We're good. Um, so yeah, instead of is that how I did it here? Did I say? Yeah, so we're going to modify the list in place instead of actually returning something. So this is just saying, when I get down to a single element, do nothing. That sublist of length 1 is already trivially sorted, so we're good. Okay. So, okay, that leaves us with the inductive step. And in the inductive step, I get to assume that merge sort helper works for all values of n. I guess I shouldn't have called it n here, up to and excluding the length of list, right? Because that's the case that we want to solve. Yeah? So now we handle the inductive case. And so, okay, sure. How did this algorithm work exactly, right? We were splitting it up, sorting each of the sublists, and then whoop, merging them back together in one case, right? So what should I call? I'm going to have some recursive call to merge sort helper. What should that call be? Does anyone want to take a guess at how I should do this? Is there only going to be one call to merge sort helper? Maybe that's the first question. Do we think there's going to be one call? I see some head nods no. Pourquoi? It's because there's two sublists, right? So I have to call it twice. Okay, so I know I have to call this merge sort helper thing twice, right? But what am I going to call it on exactly? Well, I want to split my list up in two, right? And the split point is going to be it's going to be the midpoint of low and high, right? Because if low and high is the chunk of my list that I want to sort, then I just need to sort the first half and sort the second half and then recombine them somehow. So let's compute what the midpoint is. We're going to say mid is equal to high minus low. I guess it would be technically low plus high over 2. And I'm using the double backslash for integer division here, or the double forward slash for integer division. So this gets me my midpoint. And now what I'm going to want to do is I'm going to call my merge sort helper on list from low up to the midpoint, and then merge sort helper from on list from the midpoint up to high, right? But am I done? Am I done here? Because what we've done so far is we have some list and we've split it in two, right? And by the magic of recursion, I know that merge sort helper works on any sublist smaller than n, everything in the list, right? So I'm saying, okay, this is going to be mid. So sort everything in here and sort everything in here. But is that enough? Will the whole list be sorted if I do that? Not necessarily, right? Because I could have like, sure, this could be sorted, right? In other words, let's say the list that I have in the beginning is like 12, 3, and then 6, 2, and 10. Right? So when I do my merge, when I split this up, I'm saying, okay, sort everything in here, sort everything in here. So after my recursive call, this ends up looking like 3. Oh, do it this way. 3, 12, 2, 6, and 10. And so each of these sublists is sorted, but the whole thing isn't sorted yet, right? Because, well, 12 is bigger than 2, right? So the work that's left for me to do in the inductive step after I've made my recursive calls is I need to combine these sorted sublists into one big sorted list, right? And this seems like it could be a lot of work, but it's way easier. Like sorting when you just have 2 already sorted sublists is way easier than sorting the whole list when it could be in any order, right? And there's a really simple algorithm for doing this, and I'll illustrate it right now. So if we know already that we have 3, 12, 2, 6, and 10, and my goal is to combine these 2 sorted sublists into one big list, then I'm just going to keep track of 2 pointers. Okay? And what I'll do is I'll always compare each of these 2 pointers, and whichever integer is smaller, I'll add that to my new merged list and then move that pointer forward 1. So the first time I do this, 2 is less than 3. So 2 goes here, and I move this pointer up. Okay. 3 is less than 6. 3 goes here, and I move this pointer up. 6 is less than 12. 10 is, so I go here, and then 10 is less than 12. And once I've reached the end of one of these sorted sublists, I just add everything else in the other list, which in this case just ends up being 12, right? So you can see that took O of n time, right? Because I only had to look at each of these elements once. When you know that both of this, like your list consists of 2 sorted sublists, you can combine them into one sorted list in O of n time, right? So that's all that there's left to do here, is to do this combining or merging step. And that's what we're going to do next. So, okay, now we have to handle merging the sorted sublists. And the way we're going to do that is we're going to say, all right, I'm going to have some pointer. What did I call it in my solution? I just called them I0 and I1. Okay, but we'll call them L and R here. So we're going to say L is going to start out as low, okay? And R is going to start out as mid. L and R, these are my names for these 2 indices of pointers, right? Yeah, question.
Like points sorted, and then sort the 2 sublists, and then put them in the same list, and then resort the final list.
Good question. Good question. Yeah. Well, the question is, and I'll repeat it, is why can't I just, once I have these 2 sorted sublists, put them all into one sublist and recursively call merge sort on that whole thing, right? And the reason is because what recursion provides you with is it can magically solve any problem of size strictly less than n, right? But here we're actually trying to solve a problem of size n. Like it works. This is the trade-off, the guarantee, and the blessing and the curse of recursion. The blessing is you can recursively call your function on any strictly smaller problem, but it is your job to solve it for the full problem of that size, right? Okay, so let's see how to do this now. So we have L is going to be, or my left pointer, L is going to be equal to low, and R is going to be, it's going to start out as mid. And then we're just going to say, well, while L is less than mid, right? Because that's the point at which I want to stop iterating through my left list is when I reach the midpoint here. And R is less than high, right? So as long as neither of these pointers have reached the end of their respective sublists that they're indexing into, then I'll just do the comparison that I described to you, right? I'm going to say if list sub I or list sub L is less than list sub R. And here's how you'll notice that as we were stepping through with these pointers, we were adding things to a new list, right? This merged list. So I'm going to also define a new list that I'll call merged, and it'll start out as an empty list. Okay. And then we'll say, okay, while neither of these pointers is done, we're going to say merged dot append. In the case where L is the smaller thing, merge dot append list sub L. And otherwise, in the case where L is greater than or equal to, then we'll add R or list sub R. Okay. All right, so when I reach the end of this loop, it's because either L is at the midpoint or R is at the high point. And in that case, I just add what's left in the other list, right? So now I'll say while L is less than mid, just add everything else. Merged dot append LSTL. So this is just add what's left in the left sublist, if applicable. And then we'll do the same thing with the right sublist. You'll note that only one of these two while loops is ever going to actually run. Delete word in the right sublist. The right. While R is less than high, just keep adding things, whatever's left in the right sublist. Okay? And at the very end, once I've created this merge list, I just need to replace what was in my original list with it, right? So to do that, I'm going to write list from low to high, right? This is using this slice notation because you can also use it for assignments. I'm saying reassign the portion of list from low to high to be equal to merged. And that's my whole function. That's the whole thing. And I guess I can, if we actually try and run this, do this. Terminal. Thank you, thank you. Whoa. So if we try to run this now, probably get a bunch of angry Python. Merge sort.py. Oh, wow. Okay, wow. No syntax errors. Let's see if it actually works. Python 3. So we'll just create a random new list. I don't know, that looks like. Yeah, maybe we could do this example here, 312. We can do the version, the example, it was 12.8.9. Whoa. So it's going to be a new list, which is 12, 8, 9, 3, 11, 5, and 4. Nope, that's not what I wanted. And now if I actually try and import, so from merge sort import merge sort. And I try calling merge sort on this list. Oh, whoa. Got very angry. But why? What went wrong here? Yeah, I see a hand.
Fine. Fine.
When did we define low and high?
What?
Oh, yeah. So it knows what those are because we're feeding them into the recursive subcall here, right? Like the halving takes place because mid replaces high in the left subcall and mid replaces low in the right subcall. Yeah.
The helper function doesn't have a return.
Oh, yeah. I guess. Well, it's okay here that it doesn't have a return because like in the actual version that I wrote that works, it doesn't have like that, I don't think is the issue. Not sure where it's. Oh, I know what it is. Okay, I see. We forgot to do something important. We forgot to actually update what L and R are. So L is going to be equal to, it's going to be plus equals one, right? And R plus equals one here. Because we actually, this isn't a for loop. We need to manually update these things. Um, and so we'll do the same thing here. And we'll do the same thing, R plus equals one here. And I think normally this should work now. If we do this again, we try to merge sort on our list. Ah, it's still angry at me. But why? What have I done? Maximum recursion depth reached. It's because I'm not bottoming out correctly. I don't know why. Oh, it's because this has to be one. My base case is when it's of size one. So if I do this now I try to do Python 3, this, this. Okay, it's still angry at me. Well, I'll figure this out. But there's like a version of the code that actually works that I will upload today. And it's exactly, what we've written here, minus whatever mysterious issue I can't seem to detect right. Oh, wait, I know what it is. I see it. I see it. It's here. We were dividing high by 2 and not actually getting the average correctly. So now, for sure, oh, there's no way this doesn't work. Yeah?
Why should and mark your the iron slows? If it's one means there's two elements.
Oh yeah, I think that's correct. This was right the first time around, and I said if n equals 1 or n equals 2. All right. Um, oh, I think it's because it's exclusive, right? That's kind of the convention that we had for this. Or n equals 1. Yeah, I don't think this case would ever take place actually, now that I'm thinking about it. Because they need to be different because it's exclusive, right? Like if I want one element, I need that element's index plus one, right? So I don't think this will ever happen, like this case here, but I'll leave it in just in case I'm making a mistake. Okay, now, by the power, let's see. Let's see if this works. This one's for all the marbles. We're already 1 minute over time. Okay, drum roll, please. Someone. Thank you, thank you. Whoa, it did it. It sorted the thing. So yeah, that's merge sort. Yeah. Okay, cool. So yeah, I'll upload all the code that we looked at today. Yeah, as I said, assignment will be released today. Solutions for the quiz will be released today. Wednesday's just review. And for anybody who came in later, Friday's lecture, we're gonna have a couple extra like grad student guest lecturers who are going to come in and talk about their research. So look forward to that. Okay, yeah, see you guys Wednesday. Enjoy your week until then. Uh, that's all, folks. Man.